Namaskar, welcome to Sai Economics Point. In today's lecture, we will discuss utility maximization and its mathematical derivation. Okay, see, suppose that suppose that the consumer the consumer consumes. Okay, suppose the consumer consumes two commodities two commodities X and Y, given given their prices px and py. Okay, by spending level of given money income, by spending level of money income m, okay, which is constant or given. Okay, thus the objective, okay, so the objective of the consumer is is to maximize his utility function. Okay, utility function subject to his limited income, okay, and market prices. Okay, now we'll formulate the utility maximization problem as, okay, as maximize, okay, u equal to function of x y, okay, which is your equation number 1 and which is your utility function. Okay, so our problem is to maximize the utility function, which is our objective. Okay, and subject to pxx, okay, plus pyy equal to m, which is your budget constraint. Okay, because income is limited and he is not able to purchase unlimited amounts of the commodity. Okay, so the consumer's budget constant can be given as pxx plus pyy equal to m. Okay, so this is your equation number, okay, 2, which is your budget constant. Okay, this is your budget constant. So now this can be written as m minus vxx, okay, minus pyy equal to 0. Okay, see here, u represents the level of utility, f represents the functional relationship. Okay, and what is x? S is the quantity of a good x, okay, and y is the quantity of a good y. Okay, px is the price of a good x, okay, and py is the price of a good y. Okay, and this one px into x represents expenditure on good x, okay, and pyy, this represents expenditure on good y. Okay, so this total sum of this and sum of this represents the total expenditure, that is equal to your limited money income. Are you getting my point? Okay, now okay, now okay, multiplying the constant, okay, by by Lagrangian then multiplier, it becomes lambda into m minus px x minus pyy. Okay, okay, so taking Lagrange function, the composite function becomes z becomes u of x y, that is utility, which is a function of x, y plus lambda into a minus pxx, okay, minus pyy, okay, which is your equation number 3. Okay, say here lambda represents here undetermined multiplier. Okay, now uh, conditions for consumers equilibrium. Okay, conditions for consumers equilibrium. Okay, generally there are two conditions. One is your first order condition, which is known as your necessary condition. Okay, what is the necessary condition? The necessary condition states that, okay, indifference curve must be tangent to the budget line. Okay, indifference curve, okay, indifference curve, here indifference curve, okay, must be, it must be tangent to the, okay, tangent to the budget line. Okay, or you can say slope of phi c is equal to the slope of okay, slope of budget line. Are you getting my point? Slope of phi c equal to your mrs xy. Okay, or you can write mu x by mu y. It must be equal to the price ratio, which is equal to the slope of the budget line. Okay, so at the point of equilibrium, the necessary condition, that is the first order condition, must be satisfied. Okay, that is indifference curve must be tangent to the budget line, or you can say slope of indifference curve equal to slope of a budget line. Okay, or you can say the ratio of the marginal utilities must equal to the ratio of prices for maximization of a utility. Okay, now second order condition. Okay, second order condition are sufficient okay, sufficient condition. What is the sufficient condition for equilibrium? Say at the point of equilibrium, IC must be convex to the origin. So second order condition states that at the point of equilibrium, indifference curve, okay, it must be convex to the origin. So it must be convex to the origin. That means the slope of indifference curve, that is mrs xy, it must be greater than 0, or the second order derivative of y with respect to x, it must be positive. That means slope of mrs is positive. Okay, see in this figure, okay, AB represents your budget line, okay, and IC1, IC2, IC3, this represents your indifference curve. Okay, say at the point of at point E, okay, both the conditions are satisfied. That is the first order condition. It states that indifference curve must be tangent to the budget line. See, here indifference curve IC2, it is tangent to the budget line AB. Okay, so here the slope of indifference curve is equal to the slope of the budget line, that is mrs xy is equal to slope px by py. Okay, and at that point, a second order condition, that is a sufficient condition, is also fulfilled. Okay, that is at this point, see IC is convex to the origin. That means slope of mrs xy is greater than 0. That means its slope is positive. So here that means at the point of E, both the conditions for consumer's equilibrium, or you can say maximization of utility, is satisfied. Or you can say the secondary condition of maximization of utility function subject to budget constant, it requires that the border Hessian determinant, it must be greater than 0. Then next we will discuss the derivation of first order condition. Okay, say the first order condition, the, okay, the first order condition, the first order conditions are, okay, obtained okay, by the first order conditions are obtained by setting the first order, partial derivatives, partial derivatives with respect to x and y, okay, is 0, okay, that is del z by del x, which is equal to zx equal to 0, or del z by del, okay, y is equal to zy equal to 0, or del z by del lambda, that means partial derivative of the composite function with respect to lambda is equal to z lambda is equal to 0, okay. As we know, our composite function z equal to u of x y plus lambda into m minus pxx minus pyy, okay. So now set the partial derivative with respect to x, with respect to y, and with respect to lambda is equal to 0. So now find out the first order partial derivative of the composite function with respect to x. So it is del z by del x equal to 0. So this equal to del by del x of u of xy plus lambda into m minus pxx minus pyy, okay. So this equal to 0, okay. So this becomes here del u by del x, okay. With respect to, we are deriving the first order partial derivative with respect to x, so this becomes del u by del x, okay. Minus lambda px is equal to 0. So this becomes your delta u by delta x equal to lambda px, okay. So this becomes lambda is equal to y dx whole divided by px. So this becomes your equation number, so this is your equation number 4, okay. Now set the partial derivative of z with respect to y is equal to 0 and find out the value of lambda. So next is del z with respect to y is equal to 0. So this will become here del by del y of utility, which is a function of xy plus lambda into m minus pxx minus pyy, okay, is equal to 0. So this becomes here delta u by delta y minus lambda py equal to 0, okay. So this becomes here what delta u by delta y equal to lambda py, okay. So this becomes here lambda equal to delta u by delta y whole divided by py, okay. So this becomes your equation number 5. Now find out delta z by delta lambda, that means partial derivative of the composite function with respect to lambda, okay. So this equal to 0. So this becomes here t by d lambda of u of x y plus lambda into m minus pxx minus py, okay. So this equal to 0. So this becomes here m minus pxx minus py, equal to 0. So this becomes your equation number 6. So now from equation number 4 and equation number 5, we get lambda equal to delta u by delta x whole divided by px is equal to delta u by delta y whole divided by py, okay. So this becomes here this one is nothing but here mux, or you can say ux. So mux by px is equal to, this one is here mu y by py, or we can write mux by mu y equal to px by py, or this is nothing but your mrs xy is equal to px by py, what is this? This is the slope of indifference curve is equal to the slope of budget budget line. So our first condition, that is the slope of indifference curve is equal to the slope of budget line, or the indifference curve must be tangent to the budget line, it is satisfied. So equation, so this equation, that is your equation number 7. Okay, so this equation states that the first order condition of utility, okay, utility maximization requires that, okay, the ratio of marginal utilities of x and y, okay, to their prices should be equal. Okay, uh, the second order condition states that, or the sufficient condition states that, okay, at at the point of equilibrium, say at the point of equilibrium, okay, IC must be convex to the origin. Okay, must be convex to the origin, or you can say slope of MRS xy is greater than 0. Okay, so, or you can say slope of MRS xy is greater than 0, or you can say the second order derivative of y with respect to x, it is greater than 0, or the second order condition of maximization of utility, okay, that is subject to the budget constant, it requires that the border Hessian determinant, it is should be greater than 0. Okay, so the border Hessian determinant, how can we represent it? The border Hessian determinant is equal to, you can write here, say like that, px py, px py, this is the border. Okay, so here we can write, okay, z x x, z x y, okay, z y x and z y y, it should be greater than 0. Are you getting my point? Okay, here what is z x x? Z x x equal to the, here is your second order partial derivative. Okay, so z x x equal to, okay, this is your d square z by dx square, or you can say d by dx of dz by dx. Okay, and z xy equal to d square z by dx dy. Okay, or d by dx of dz by dy. Next, z yx equal to d square z by dy dx, or how can we find it? D by dy of dz by dx. Okay, now z y equal to d square z by, okay, dy square. So this equal to del y of this one by dy. Okay, are you getting my point? So now evaluating, okay, the Hessian determinant, we will get what, we will get, say, how can we extend the determinant? Say, by evaluating the determinant by extending first row, say this is 0, something multiplied by 0 is 0. Okay, so this becomes your 0 minus, next, say next one is minus px into this row, this column deleted, so this one is multiplied with this and minus this one into this. The next minus py into this row, this column deleted, px into lyx, okay, or sorry, zyx, and minus this one py into zxx. Okay, so this will become here 0 minus px into px into px zyy minus py zxy, okay, plus py okay, plus py into what, px into zyx minus py into zxx. Okay, now simplify it. Okay, so this becomes your 0 minus px square, okay, z y y, okay, plus px py, okay, px py z x y plus, see here, px py z y x minus what, py square z x x. So this equal to your 0 minus px square z y y. As z x y equal to z y x, so we can write here plus px py z x y plus px py z x y minus py square z x x, as z x y equal to z y x. So this becomes your minus uh, minus px square z y y, okay, plus 2 px py u z x y, okay, minus py square z x x, okay, or we can write this equal to, so this equal to your 2 px py 2 px py, okay, z x y minus, okay, px square z y minus py square z x x is greater than 0, or your border Hessian determinant is greater than 0, or you can say here the second order condition, that is the at the point of equilibrium IC must be convex to the origin. If this condition is satisfied, then our second order condition is fulfilled. Okay, so utility is maximized where the first order condition is satisfied, that is IC slope of IC is equal to slope of horizontal line, and the second order condition, that is border Hessian, the determinant of the border Hessian is greater than 0. Okay, thank you, have a nice day.